The other main type of potential energy that we're going to look at in this unit is gravitational potential energy. And this is the energy that's related to gravity. So if we come over here, just like before, we're going to talk through all of the bits and pieces. So this is the energy associated with the arrangement of an object and the Earth. So the arrangement of object and the Earth. So if they're in a different position, we're going to see a different amount of gravitational potential energy. And the properties, that's a typo up there from when I copy pasted. I should say gravitational. So the properties, as with all energies, it's a scalar quantity. The variable we're going to use for gravity is UG. Just like with elastic potential energy, the U for the potential energy, and then the G to specify that it's gravity. The units, like all energies, are in joules. And as a quick reminder, 1 joule equals 1 Newton meter equals 1 kilogram meters squared per second squared. And the equation that we use for UG is equal to mg times the change in height. And again, that's a change. And this is when we're close to Earth. So if you're dealing with a problem that's, on the surface of the Earth, or someone's throwing a ball up in the air, that's what we consider close to the Earth. Basically, if G is a constant, this is fine for using that. So the constant is mg, or in other words, it's actually the weight of the object. And the indicator is h, or the height. So if something moves higher up, farther from the Earth, then you'll see the potential energy increase. If it moves closer to the Earth, farther down, then the potential energy will decrease. So here's an example. For a given building, assume the vertical distance between floors is 4 meters. How much gravitational potential energy is gained by a 10 kilogram, that's supposed to say box or book or whatever you want it to be, that is moved from the ground to the first floor, 1 floor up? How much is gained from moving from the first to the fifth? What about from the fifth back to the third? So in case 1, UG equals mg. The change in UG is equal to mg times the change in h, which is mg times h of floor 1 minus h of floor 0, which is equal to 10 kilograms times 9.8 meters per second squared times 4 meters minus 0 meters. And that will give us 40 times 9.8 joules. So that's approximately 400 joules. More accurately, it'll be, we can do that pretty easily. It's 0.2 less, so 0.2 times 40 is 8. So it should be 392 joules. For our second problem, moving from the first floor to the fifth, so delta UG is equal to mg delta h is equal to mg of the final height, so height of the fifth floor minus height of the first floor, is equal to 10 kilograms, 9.8 meters per second squared, The height of the 5th floor will be 20 times 4, sorry, 5 times 4, giving you 20, minus the 1st floor, which is just 4. So that will be 16,160 times 9.8 joules, and 0.2 times 160, so this would be 1600. 0.2 times 160 would be 80, no, 32. So 1,600 minus 32 would be 1,568, I believe. Double check that just in case, but that's what we get there. And then for 3, from moving from the 5th floor back to the 3rd floor, delta UG is equal to M times G delta H. Delta UG is equal to mg times the height of the 3rd floor is our final, minus height of the 5th floor. So that will be equal to mg times 3, which will be 12 meters, minus 5, which is, we said 20 meters. So that will be 80 times 9.8 joules. Sorry, 800 times 9.8 joules. And that will end up giving 0.2 times, no, it was 80. 0.2 times, wow, I really messed some of these up. Sorry, no, I didn't. 80, 800 minus 16, so 7. 784 joules. And it's negative, though, because 12 minus 20 gives negative 80. Okay, so that's a couple of quick examples. And again, we can only ever calculate changes in gravitational potential energy. The AP sheet does show this, which is nice. But if you ever hear, or if they ever ask, like, what's the gravitational potential energy of something, that's comparing to some standard reference, usually the ground or sometimes the starting position, and setting that as 0 and then just calculating above or below that. But really, again, we should be calculating changes at all points in time.